Artemis III, as it stands today, does not exist as a launch event or a countdown on a public screen. It exists as an evolving architecture inside NASA's planning systems, a mission still being designed, reviewed, and reshaped based on the lessons of Artemis II. The United States is not simply preparing to send astronauts back to the moon. It is building a new operational framework for deep space exploration where every system must prove itself before it is trusted with human life. Just 2 weeks after Artemis II successfully returned to Earth, the entire focus of NASA shifted forward, not toward celebration, but toward refinement, data analysis, and the next critical step. Artemis III has become the center of that effort, not as a flight yet, but as a complex test of readiness, precision, and control. The foundation of Artemis III is directly shaped by what Artemis II revealed. The previous mission confirmed that the space launch system and Orion spacecraft can operate in deep space conditions and return astronauts safely to Earth, which is a historic achievement in itself. But in space exploration, success does not end uncertainty, it expands it. Engineers are now studying every data stream from Artemis II, searching for subtle patterns in thermal behavior, propulsion consistency, communication timing, and structural response. These details matter because Artemis III is not a repetition of the past. It is a more demanding version of it, where systems are expected to operate for longer durations, under tighter margins, and with more complex mission objectives. The planning teams are not asking whether the system works, they are asking how it behaves when pushed closer to its absolute limits. At the center of this mission stands the Space Launch System, the most powerful rocket NASA has ever built. But in Artemis III planning, it is not treated as a finished product. It is treated as a system still being optimized for human-rated deep space missions. Every component is under continuous review. The solid rocket boosters must demonstrate predictable thrust behavior across varying conditions. The core stage must maintain stability under extreme aerodynamic pressure. The avionics systems must respond instantly and accurately to real-time flight changes. Even the smallest delay or variation in performance is analyzed in detail because once Artemis III launches, there will be no opportunity to correct mistakes in real time. Above it all sits Orion, the spacecraft designed to carry astronauts beyond Earth orbit. Its heat shield, life support systems, navigation computers, and communication arrays are all undergoing refinement because Artemis III will expose them to longer mission cycles and more complex operational demands than ever before. Unlike earlier eras of space exploration, Artemis III is being developed in a much more compressed and urgent environment. The United States is no longer working alone in space. Instead, it is operating in a competitive and collaborative global environment, where private companies now play a critical role in deep space infrastructure. The lunar landing systems required for future missions are being developed by multiple partners, including SpaceX and Blue Origin, each bringing different engineering approaches and design philosophies. This means Artemis III is not just a government mission, it is a coordination point between multiple technologies that must function together flawlessly. The mission is designed to test that integration in orbit before any attempt is made to land on the lunar surface. Inside NASA's mission planning centers, the structure of Artemis III is being built with extraordinary precision. Every phase of the mission is mapped out in detail, from launch to orbital insertion to docking, simulation, and return. The mission is not divided into separate events. It is treated as a continuous sequence of interdependent operations where each phase depends entirely on the success of the previous one. The space launch system must deliver Orion into orbit with exact precision. Orion must then navigate and rendezvous with the human landing system already positioned in space. The docking process must occur without deviation or error. The combined system must then simulate lunar operations under realistic conditions before safely returning to Earth. Every step is designed to test not just hardware, but the entire operational philosophy of Artemis as a program. The astronauts selected for Artemis III are already deeply involved in training. Even though the spacecraft is still undergoing preparation, their role in this mission is not passive. It is highly interactive and decision-driven. They are training inside advanced simulators that replicate the exact conditions of orbital mechanics, docking operations, and emergency scenarios that may occur during flight. But the focus of their training is not perfection under ideal conditions. It is adaptability under uncertainty, because Artemis III is not designed to test whether procedures work when everything goes right. It is designed to test how humans and machines respond when conditions begin to deviate from expectation. This is where real mission readiness is defined. One of the most critical phases of Artemis III is the orbital rendezvous and docking sequence. After Orion reaches Earth orbit, it must navigate toward the human landing system, a spacecraft developed by private industry and positioned independently in space. This is one of the most technically demanding operations in the entire mission. The two spacecraft are moving at extremely high speeds, each following precise orbital paths that must be synchronized with mathematical accuracy. The process of closing distance between them requires constant adjustments in velocity, orientation, and trajectory. Even the smallest misalignment can result in mission failure. This is why this phase is considered one of the highest risk and highest value components of the entire Artemis III architecture. Once docking is achieved, the mission transitions into its most experimental and mission-defining phase. Astronauts will transfer into the human landing system and begin full operational simulations of lunar descent and surface procedures. They will not physically land on the moon, but they will perform every action as if they are preparing to do so. This includes testing descent control systems, simulating landing trajectories, practicing surface operations, and executing emergency response protocols. The purpose of this phase is not demonstration, it is stress testing under realistic conditions, because systems that function perfectly on Earth or in simulation often behave differently when integrated into full mission environments. This is where Artemis III becomes essential. It exposes weaknesses before they can become real failures. Another major component of Artemis III is the validation of next generation life support systems and spacesuits. These systems are designed for future lunar surface missions, where astronauts will operate in environments with no atmosphere, extreme temperature variations, and constant radiation exposure. The suits must support mobility, communication, temperature regulation, and life support simultaneously. They must function as independent survival systems, not just protective gear. Artemis III provides the first opportunity to test these systems in a realistic orbital environment, where astronauts can evaluate how they perform during extended operational scenarios. This data will directly influence future lunar surface missions and long-duration exploration strategies. As the mission continues toward its final stages, the focus shifts toward return and re-entry. This phase is one of the most physically demanding and technically critical parts of the entire mission. Orion must re-enter Earth's atmosphere at extremely high velocity while maintaining structural integrity and protecting the crew inside. The heat shield becomes the most important system on the spacecraft, dissipating extreme thermal energy that can reach thousands of degrees. The performance of this system is especially important because previous missions have already revealed subtle variations in thermal behavior. Artemis III is expected to provide the most comprehensive real-world validation of these systems under actual deep space return conditions. Ultimately, Artemis III is not defined by a launch date or a single event. It is defined by a continuous process of preparation, validation, and integration happening right now inside NASA and its global partners. It represents a transition point in human space exploration, from experimental missions to structured operational capability. It is not about reaching the moon directly. It is about proving that the systems required to reach the moon repeatedly, safely and reliably actually work under real conditions. For the United States, this mission represents more than a technical milestone. It represents a shift in how humanity approaches space itself, not as a distant frontier to visit occasionally, but as an environment to operate within consistently, carefully and permanently in the future.